Okay, folks, section 2.5 is going to discuss reasoning in algebra and geometry, and this is the foundation for our proofs that we're going to start to encounter in the next several weeks. And when we talk about reasoning, it's why do we know what we know about something? Okay, and it's a logical analysis of some statement. In order to actually do like coherent logic and make coherent arguments about the validity, the truth of a statement, we have to have some underlying principles that we all agree upon. Okay, so we've got to have our knowledge of our properties of equality. These are things that you have used to solve equations. And they're all provided with abstract variables and operators, but we can plug in specific values for A and B and C through these and show that these are legit properties and that they make sense. Your addition property, says if A equals B, then A plus C equals B plus C. Well, if 3 equals 3, okay, I have 3 here and I have 3 here, and I'm going to add C to both sides. So let's say C is some other number. Let's say it's 5. Do I still get a truth? This was true. Is this still true? It absolutely is. So the addition property that you guys have talked about in solving equations says if I add something to the if the two things are equal and I add something to the left-hand side, then I have to add it to the right-hand side to keep that statement true or balanced. So if I have 2x minus 3 equals 12, okay, we use the addition property of equality all the time here because we're going to add 3 here and add 3. This is saying that sum A is equal to sum B, and if I add C to both sides, my result should still be equal. Those two things, because I added the same amount, some C term to both sides, that is still true. Okay, so that's kind of where we see the addition property. We know that the same thing occurs then with subtraction, because subtraction is adding the opposite. So subtraction is actually defined through addition. So if this works for addition, it works for subtraction. Multiplication property says, if I start with two values that are equal and I multiply them or amplify them by the same amount, I should still yield two things that are equal. So again, if I start with 3 equals 3, so then I multiply 3 by, let's say, 2, I still get 6 equals 6. That's still true. Where you've seen this the most would be something like if I have 1/2 x equals 5, that's an A right there. That's my B. If I multiply this side by 2, multiply this side by 2, I get something new. I get 1x is 10. But because I did the same thing to both sides, we're okay. Okay, we still get a true statement. Division property is the inverse of that. So basically telling us if I have two things that are equal, if I have 2x equals 10, as long as I divide by something that is not 0, because we can't divide by 0, because I divided both sides by the same thing, I get an A over C, which in this case would be 1x, and 10 over 2 would be 5. This is still true, because that was true, and what I divided by was the same thing. So we know those things. Okay, those are hopefully ingrained in your skills and memory to where you never forget them. Some of the ones that we're not comfortable with or familiar with is the reflexive property. The reflexive property you actually use all the time. It's essentially saying that this thing, the C that we were going to add to both sides, or the C that we're going to remove from both sides, is indeed the same amount. So a lot of people, like when we're given this, I'm going to say that's my first statement, and I know it's true because it was given to me. So that says given. Next thing people usually do is they're going to say, okay, well, I'm going to add 3 to the left-hand side and 3 to the right-hand side. So when we do it by hand, and we just put like +3 here, +3 there. And what we're really doing is saying that the amount that I'm going to add to the left and the amount that I'm going to add to the right is indeed the same thing. 3 does equal 3. And that's the reflexive property. Whenever we say something is equal to itself, it's reflexive. The way I kind of remember the property is that it sounds like reflection. And if I think about like my equal sign being a mirror, this side here is what I start with. Here's my mirror, and here's the reflection. And when I look in a mirror, my face and the reflection should be the same thing. The symmetric property, you guys use the symmetric property all the time. Let's say I had an equation that was like 3 equals, let's say, 2x minus 9. You're going to add 9 to both sides, and you get this. And then you can go and divide both sides by 2, and I'm going to get this. And then a lot of people say, oh, I like to rewrite it this way. But what we just did was, if 6 equals x, then x equals 6. It's exactly what this is saying right here. Where a is my 6, my b is my x. Then I can say b, which was x, is the same as 6, which was my a. You can flip an equation and still have a true equation. That's all the symmetric property says. Symmetry, what symmetry means, if I draw a line down my face or my body, my left-hand side should map to my right-hand side. Okay, they say that people that are beautiful have perfect symmetry. Okay, or the most beautiful people have perfect symmetry, or very close to perfect symmetry. If I were to draw a line right here through the word then, now the letters don't match up, but that B is going to fall on that B, and that A is going to fall on that A, and that's kind of how we deal with symmetry. I don't know if you guys have ever done this in like an art class or something like that. You take a piece of paper and you're going to crease it in the middle, and then you put like a blob of paint here, and then maybe a different color blob of paint there, and then maybe one down here. And then you fold on this line and smear it together. And when you unfold it, the image that is created here on the left-hand side is exactly the same as the images on the right-hand side. Okay, so that's a symmetric application, and the same thing happens when we're dealing with equations. We have a transitive property. So the transitive property says if A equals B and B equals C, then A equals C. If you remember the other day, we talked about the law of syllogism. It's kind of the idea here. If let's say segment AB is equal to segment CD, and CD is equal to 5. If that's what I start with, AB is equal to CD, but CD's length is 5, then what can you tell me about AB's numerical value? It should be 5 as well. CD is kind of what I call the middleman that links these two things together. Okay, so that's kind of the law of syllogism in regards to working with more numerical statements. I like the idea of saying, if, let's say we're playing basketball, and let's say, let's do this. Let's do this example. Let's say if Mr. Fay is younger than Mr. Jesko, but Mr. Jesko is younger than Mr. Shine. Okay, what can you say about Mr. Fay compared to Mr. Shine? Mr. Jesko is the person that linked us. Okay, that linked Mr. Fay and Mr. Shine. But if I'm younger than Mr. Jesko and Mr. Jesko is younger than Mr. Shine, you can make the argument that Mr. Fay is younger than Mr. Shine. Okay, and that's kind of the idea of the transitive property and the law of syllogism. Substitution property. You do this all the time with equations. If I say 2x plus 3b, and I ask you evaluate that if x equals 1 and b equals 3, well, now we rewrite this as 2 times 1 plus 3 times 3, and we get our 11. What you just did is you substituted. I told you x is 1. So wherever I see it, I can replace it with what it's equal to. Here I tell you b is 3. You can replace it over here with whatever b was equal to. I like to think about substituting. We do this all the time in sports. If player A is as good as player B, then I can take player B out of the game and put player A in. We call it a substitution. We call that person a sub. Because the idea is we're going to substitute to get the same production from both players. So we're saying that their abilities or their skill sets are equal when we do that. Distributive property, you guys are aware of. If you think about what you're doing here, the distributive property, if I take A times B, I get AB, take A times positive C, I get AC. All you're doing when you're doing the distributive property is you're multiplying, okay? So the distributive property is simply a fancy word for multiplying. Distribute means to give out. If I'm a paper boy, I distribute the newspaper to my customers, meaning that I give each one of them a paper. We can distribute to a difference, or we can distribute to a sum. We can even do this, which you guys have done before, A plus B, and let's say I've got then C plus D. Okay, all this is, so you would FOIL this if you remember, but think about what's going on here. FOIL means first times first, so you would do that, and then outside times outside, so you would do that. And if you think about that, that image looks just like what I've done here. Okay, then you would take B times C, so that's your inside times your inside. It is B times D, that's your last times your last. Okay, so all that means is that you are, when we FOIL, we're actually distributing twice. Okay, we can distribute, if I have A and then I have B plus C plus D. All that means is I'm going to distribute, I'll get AB plus AC plus AD. Okay. There are also times, and you're going to see this in your homework, that something looks like we're combining like terms. Okay. If I say I have 2x plus 30 plus x equals 180, and I rewrite that as 3x plus 30 equals 180, in your homework it's going to ask you to choose that as the distributive property. But kind of let's talk about this real quick. I'm just going to come over to side and write 2x plus 30 plus x equals 180. Okay, and this is maybe something you guys have done in some of your algebra classes. They do a little bit of a mini proof on why x is, whatever value we get down here in a moment. If you've been in other classes, sometimes you would do something like this. I'm going to go ahead and I'm going to rewrite this as 2x. Let's do it this way. This might make more sense. Let's go x plus 2x plus 30 equals 180. And I'm going to keep the parentheses around those two. So all I did was I moved this x out in front. And if you remember the property that allows you to move things, it's called the commutative property. So this is this isn't called an algebraic proof. And all we do with a proof is we write something that we know to be true, but then talk about over here, how did I know it was true? What allowed me to do what I did? Okay, so the commutative property allows me to do that. Now, a lot of times we would then say, okay, well, I'm going to do this. I'm going to change my parentheses and write it this way. And if I change my parentheses, I group things differently. You remember that's the associative property. And these are of addition because there's commutative property of addition, commutative property, or the associative property of addition here. And then, like x plus 2x, we would rewrite that as 3x plus 30 equals 180. And a lot of people would write combine like terms. Okay, and that's a valid argument. Okay, that's what you were taught that it was called in algebra. But let's talk about this real quick. If I go x plus 2x, x plus 2x, why is that 3x? And people will say, oh, because when we have like terms, because we know what like terms are, when we have the same variable with the same exponents, we add the coefficients out front. We know what coefficients are, they're the numbers out front. And I would say, yeah, that's exactly what we do. But then I'm going to ask the question, why do we do that? Because you really haven't answered why. You answered what you've been told to do, or the structure of what you've been told to do and how to do it, but you don't have the why yet. And the why that this becomes 3x is this right here. My hope is that you could argue that working my way backwards, I could rewrite this phrase right here as x times the quantity 1 plus 2. And the reason I can write that is because we have knowledge about the distributive property. If I were to apply the distributive property to this, x times 1 is that 1x, and x times a positive 2 is that 2x. So, by doing this, or starting this, I can rewrite it this way, and now my order of operations tell me look inside those parentheses, and you can rewrite that as a sum of 3. And now we have a variable times a number, so we rewrite that as 3x. So the question is, why is 1x plus 2x 3x? It's not because, well, when we have like terms, we add the coefficients, or we have the same variable, we add the coefficients. The reason that 1x plus 2x is 3x is the distributive property. So we're able to pull that x out, see that that leaves me with 1 plus 2, add those together, and then multiply that x back in. So a lot of times when you think that you're combining like terms, especially with variables, the result is the distributive property. The logic or the reasoning is the distributive property. Here are some properties about congruency. These are some things that we already know. We already knew that A was equal to A. That was the reflexive property, and A stood for a real number. Now what we're saying is that if I have a segment drawn in front of me, I have segment AB. Well, if I have segment AB, it is congruent to itself. I can cut and paste AB and put it back on top of itself. Okay, we can maybe demonstrate that. Control C, V. I can take that segment, AB, put it right on top of itself, still have AB. Okay, so we have the reflexive property with actual shapes. Same thing with angles. Okay, symmetric property exists if I have AB is congruent to CD, or segment AB is congruent to segment CD. If I need to or have a reason to, I can flip-flop it and say segment CD is congruent to segment AB. Okay, so congruency is much like equality in regards to this kind of being a two-way street. You can read it left to right or right to left, and it still be true. Transitive property, same idea. Okay, if angle A is congruent to angle B, and then angle B is congruent to angle C, then I can say angle A is the same as angle C. So let's kind of draw a picture of that real quick. So let's say I've got this angle A here. Do one more. Oh. All right, so if I've got angle A here and angle B, and we know they're congruent, hopefully you can argue that because I cut and pasted them, but they are congruent. They're the same shape, same size, so they are congruent. And let's say I've got angle C here. Okay, would you agree that B and C are congruent? Okay, so A was congruent to B, but B is also congruent to C. So by our law of syllogism and our logic and essentially the transitive property, I don't have to take A and put it onto C to see if they're congruent. I automatically know that they will be. And it's the transitive property that allows that to happen. To prove it though, A and C do match up. So if A is congruent to B, but B is congruent to C, then A is congruent to C. Basically what the transitive property allows us to do in congruency and even inequality, what it does, let's say I could take, let's say I have 1,000 things that are the same. Okay, I have 1,000 angles that I've cut out and put in a box. The transitive property allows me to essentially take any, just reach into that box, take out any two angles, and because all of them were the same, then I know that any two are the same. Okay, and that's essentially what the transitive property does. It's a linking procedure of either equality or congruence that allows me then to narrow my focus on just two of the objects in the linking system and make an argument about them in regards to congruency or equality. And that's kind of what this next slide is talking about. Okay. Let's say I have a class of 30 people and they're all the same age, and I put their ages on note cards and put them in a hat. And then I reach in, because I know all the ages are the same, when I reach in and grab any two note cards, the numbers on those note cards are going to be the same on any two. And that's essentially the transitive property. If I were to write this, let's say Faye is as old as Mr. Jesco, and Mr. Jesco is as old as Mr. Gomez, then we could say that Mr. Jesco is the link between the two, so then Mr. Faye and Mr. Gomez have to be the same. Some properties of equality and congruence. So using these properties that I just discussed, these are some examples that are going to be similar to your homework of what we are going to, or how we're going to justify what has been done in these. So initially, each of these is considered a given statement. If they're the given statement, then we ask ourselves, well, what happened to go from that statement to the second one? My hope is that you can all see we subtracted 9 from both sides. So my reasoning or my answer from what allowed me to go from here to there is that property that we did to both sides. So this would be the subtraction property of equality. Here, okay, this is given. And now, if this was true, how do I know that this is true? Well, if I think about this, it says angle O is congruent to angle W, and angle W is congruent to angle L. So here's my middleman. That's the thing that's linking O and L. So I can make the jump without ever comparing O and L, without ever putting them on top of each other or anything like that, or knowing anything about either of one of those or either's degree. Because O is the same as W and W is the same as L, I automatically know O is the same as L. That's the transitive property. And it's the transitive property because we're talking about congruency here, so it's the transitive property of congruency. Here, this is given. Okay. And I want to figure out, okay, if I started with measure of angle E is equal to measure of angle T. So what this is, guys, is when I say measure, there's a number that is representative or symbolic of. I don't know what the number is. Maybe it's 30 degrees. Maybe it's 45 degrees. Maybe it's 100 degrees, whatever. Okay? What this is basically saying, if I know the measure of angle E is equal to measure of angle T, well, that's the same thing as saying measure of angle T is equal to measure of angle E. I can flip my statement, and that's the symmetric property of equality. So these are the same thing, same type of questions. Again, number one here is given. Okay, what allows me to say if AR is congruent to TY, why then is segment TY congruent to AR? Again, that's just flipping things. So it's a symmetric property of congruence. Okay. When you have properties like this, that some are equality, some are congruence, and they're shared, like symmetric property congruence, symmetric property of equality, when you're doing like multiple choice tests, a lot of times like option 1 or option A would be symmetric property of equality for this one, because they're testing when they do standardized tests that are multiple choice like that, or even in Math Excel when guessing drop down questions, they're not judging only whether you're good at math or the content that is being asked about, but you're also aware of details. Okay, you can pay attention to details. So what they'll do is they'll try to catch you off guard by putting symmetric property equality as option A, because somebody will see symmetric right away and say, oh, that's symmetric property, and they'll choose A, but because it says equality, it would be wrong. Option B, C, or D would be the correct one. It says symmetric property of congruence. Just be on the lookout for that. Here, again, this would be given. And then, okay, well, what did I do from 3 times 20x plus 5 equals 9 to get 3x plus 15 equals 9? We did that, which that's the distributive property. This one here is given. Okay. And then the question is, and this is debatable, okay, but the best answer is if my coefficient is a fraction, then what are we going to do to get rid of that fraction? We're going to multiply by its reciprocal. So I'll multiply by 4. So I'll multiply this side by 4, multiply that by 4. So this is multiplication property of equality. Now I say it's debatable because some people will do this because we've been just entrusted with calculators and allowed to use those forever. People will do, well, I'm going to divide this by 1/4, which is okay. I mean, 1/4 divided by 1/4 does give me 1. But then they'll come over here and they'll divide this by 1/4. And on their calculator, sometimes they'll get this right, sometimes they'll get this wrong. Sometimes on their calculator, they'll type this in. They'll take 7 divided by 1, which gives you 7, and then 7 divided by 4 does not give you the 28 that we're looking for. So they get it wrong quite often. But if they put this in parentheses, they'll be okay and they'll get 28. But why is that the case? Well, if you remember your division of fraction rules, dividing by a fraction is identical by definition to multiplying by its reciprocal. So I've got the idea here is that when I have a fraction here, I want to multiply both sides. It says whenever we try to make an argument, you must have a valid reason for your argument. Okay, what statements allow you to go from statement A to statement B? And that's what we're doing up here. These are my reasons. Okay, why am I able to go from the first statement to the second statement? I have to have a valid reason. I'm going to skip over some of these other examples here. You guys can do those as you see fit. If you're struggling with the ones that we went through, there's a couple more here that are very similar. Let's see here. I'm actually going to stop this video, and tomorrow we will pick up with proofs. So I'm going to give you some practice with questions like these in your homework, and then hopefully get accustomed to that process. And then tomorrow we'll start proofs and actually kind of adjoining a bunch of statements like this together inside one problem.